Good morning. So, what we have seen earlier is the creep behavior of materials, their different mechanisms and all. We have seen earlier that the steady state creep rate or the steady state is rather the most important step of creep behavior. So, we have many, you can say, we do the studies based on the steady state behavior of a material. Now, here we have seen that steady state behavior or steady state creep rate epsilon is dot equal to, that means the steady state creep rate can be represented by one Arrhenius type equation. Okay. Why it is required? Now, it is required to know the activation energy for creep. Okay. So, if I see this equation epsilon s dot, you understand that is steady state creep rate. This is a constant, Q is the activation energy, so we understand that during creep behavior atomic diffusion takes place inside the material. So, it is temperature assisted phenomenon and there is a rate associated to this. So, this rate, that means the deformation rate type equation is there. So, we have this kind of equation where Q is this activation energy, R is the universal gas constant and T is the temperature, we know that is in absolute scale. Okay. So, if this is so, then for any creep deformation or creep behavior we can have calculation of activation energy. How do we do that? Now, say we have we did a creep experiment using different temperatures. The temperature variations should not be very high such that the mechanism of creep changes. Do you follow this? We know that earlier we have seen that if we do the studies at low temperature, then there is some certain creep mechanism. If we do the study at high temperature, then also there is some certain creep phenomenon. Obviously, here low temperature means that is above the temperature for having creep in the material. Okay. On that some lower level of temperature and then high temperature means there we have a temperature which is close to the melting point of the material. So, we have seen that dislocation assisted creep or diffusion assisted creep takes place if we vary the temperature. Now, for calculating the activation energy, we should not vary this temperature to that much such that the creep deformation mechanism changes. So, we will be doing small changes in the temperature and if we do so, then obviously we will have some different creep behavior under same mechanism. Different in what terms? Now, only the steady state creep rate will vary. Okay. So, that way if we vary, then you have this axis is the strain and here we have time, right. So, this is the nature of the curve. Now, if I take, say I have certain point here, certain point here. So, in these different regions I have different creep rate versus time. So, creep rate versus time is there. So, I can find out from here to here in the steady state what is the creep rate, means the slope of this curve we have to take. Similarly, here the slope we can take any 2 point in the steady state part of the curve, any 2 point if you take, then I will have the slope of these curves. So, I can find out from any curve what is epsilon dot. Also, we have we have the softwares by which this kind of curves, any Excel origin anywhere we fit, we can have some differentiation to this curve, and if I differentiate, then we will have the rate curve, isn't it. So, we have the rate, that means what is the steady state creep rate that we can calculate, and then this equation if I do this in this way, that is epsilon dot 1 equal to the constant e to the power minus q by r T 1 and another temperature I have epsilon dot 2 constant e to the power minus q by r T 2 we can do this, and then you just to find out Q, it will be R है ना. So, if I take log or ln both sides, we will have the Q equal to R ln this divided by 1 by T2 minus 1 by T1. Do you follow this? If you take log both sides, ln this equal to ln A plus minus Q by this, and that equal to this. So, this way if you take out Q, we will have this equation to find out the activation energy for creep. Can you follow this or not? This is very simple, I think you understand. Do you understand? Okay. So, if so, do a problem. So, the problem is very straightforward. You just put this in the equation and get the result. Rather, this is one problem which is given in Dutta's book. We have many other problems which are similar to this, there is no change, or the one that I said, that like the curve that I put here, on this the graduations will be given, you have to find out the slope and calculate. So, the value of R you can take 8.314 joule per mole per degree Kelvin. The unit of Q you may represent in terms of kilojoule per mole. So, it is very simple problem, that two different temperatures you have. Only thing you have to keep in mind that it is in absolute scale. So, whatever 700, 800 is given, you add 273, represent in terms of Kelvin. 599, na? So, Q equal to 599. You did it, all of you. Q equal to around 599 kilojoule per mole. Okay, so this is a simple problem. I am removing it off. Okay, so now how will be the creep fracture surfaces? Isn't it? We have seen that creep behavior occurs in materials. So, the creep fracture surfaces, how the cracks grow. For that we have one idea which is known as equicohesive temperature. So, what is equicohesive temperature? We will tell. You know it. So, bolo. Equicohesive temperature is nothing but at a temperature where the energy or strength of the grain boundary equal to the strength of the grain interior. Okay. So, if we are working at room temperature, or you can say at low temperature, you can say that at that temperature ranges the grain boundary is stronger than the grains. Okay. But above equicohesive temperature, what happens is the strength of grain boundary reduces, grain boundary becomes weaker. Okay. So, as creep is a high temperature phenomena of a material, so mostly for many materials it is above the equicohesive temperature. Okay. Mostly for materials it is above the equicohesive temperature. So, what we see is the intergranular types of failure. Why? Because at that temperature level, equicohesive temperature, we are working at high temperature level. So, I will have weaker grain boundary. So, if you have a weak grain boundary, then a crack which is produced can grow through the grain boundary itself. Okay. So, what we see that above ECT, grain boundary becomes weak, and that is why cracks grow through the grain boundary, and I have intergranular type fracture. So, well, we already understood earlier, and we are knowing it, that what is intergranular fracture, right, if the cracks grow through the grain boundary, etc. Okay. So, that we have seen earlier. So, we have the intergranular type of fracture and different fracture nomenclatures are there, like you please open Ditter's book, you can see this W type fracture, intergranular fracture types of creep deformation. A W type fracture, wedge shaped fracture or R type fracture, these things we can see on the materials fracture surfaces. So, that you can understand from there. Okay. Okay. Another interesting thing is there is, if I have a small grain size material. Okay. Small grain size material means what? The number of grain boundaries are more, and if we are working at a temperature which is above equicohesive temperature, so all the grain boundaries are weak. So, as the grain boundaries are weak, cracks can grow through this. So, above equicohesive temperature, if a material is fine grained, then its strength is less. If I have a big grain, we are working above equicohesive temperature, okay, then number of bigger grains are there. So, the easy crack propagation may not take place. Okay. So, above equicohesive temperature, small grained material is weaker compared to large grains, which is opposite to the cases when we are working below the equicohesive temperature, where we want to reduce the grain size to increase the strength of a material. Okay. So, this phenomena you must understand. And in the fracture surface, already we have seen earlier in our last class, I hope all of you have seen that factograph that I have given to you. Fracture surface contains many other signatures. Signatures means what? Now we can see what we can see? Some grain boundary sliding, we can see some grain rotation. Okay. Grain boundary sliding we can see, that means one grain is there that can shift towards that region. So, on the surface after creep deformation we can see this kind of phenomena. So, by looking at these things we have some idea that there is creep. Okay. Okay. Then another phenomena we have to understand related to creep is superplasticity. So, we will have little idea about it, because it is not the details is not there in our syllabus. So, why superplasticity, or why a material behaves in superplastic manner? I think earlier also I said superplasticity means the extended plastic regime. Super term is there, we call superheat movies, so which is better than heat. So, superplasticity means plasticity is higher. So, how much higher it is? Sometimes we get about 1000% also. Okay, 1000% you try to imagine. If it is 100% strain to a material, that means what? Now, a 10 mm gauge length has become 20 and it is 1000%. So, it is very big, we can say. And what is the in which cases this superplastic behavior in a material can take place? Mostly at high temperature, and some materials are there which can be deformed in a superplastic manner. So, what is the facility of that? What we will get from that? It is the thing is, say I have to deform a structure. Okay. So, if the material is superplastic, then I can bend it or do any or give any kind of shape to this. Okay. Because superplastic means it can be elongated to a very high extent. That means what? Now, without necking, a material can be deformed. Okay. This is the criteria. Superplastic means a material can be elongated without necking. Necking we understand. If there is necking, then there will be triaxial state of stress incorporating to that, and the material will fail at that extent. But if there is no necking, that means what? Now, I am deforming it, but it is not breaking, it is not getting fractured. Okay. So, a material which is superplastic in nature can be deformed to a very high extent, and that is how I can produce any required shape out of it. Okay. So, superplastic behavior is this, and it occurs at high temperature. It has to be it is having very high strain rate sensitivity and all. Okay. some material like the behavior is similar to this atta flour, okay, rye flour and all, wheat flour we can make we usually do in our home, that I have this, we take a small ball from our parents and all whoever is working and then make it, as long as you can make it, although it is not a superplastic material, but the nature looks like this. We are making it without a necking to a very large length, small ball you have taken from there, large length we can produce. So, what are superplastic materials is very easy to find, you find out what are superplastic materials, okay. What I will write, what are. So, that you find by yourself, and superplastic materials, one there are many mathematical relationships, okay. Only thing we know earlier which is quite known to us is point of instability. In the tensile chapter we have seen, where we have seen dp equal to 0. So, dp greater than 0, or we have means it is not equal to 0, we have d sigma by d epsilon equal to sigma, right. So, that is greater than sigma, d sigma by d epsilon greater than sigma, those things are there mathematically, we can write for a superplastic behavior of a material, okay, that you can check. Acha. What next? Next I have creep resistance, how to improve creep resistance. So, how to improve creep resistance? Now, here one term which is known as stacking fault energy you heard earlier, that helps. So, what is there? Now, if I can reduce the stacking fault energy of the material, then it improves the creep resistance. So, how it is working actually? Now, say I have climb during creep deformation, okay. So, during creep deformation, if I can reduce the material's stacking fault energy, then the dissociation to partials will be reduced, okay, and that way the cross slip phenomenon can be, means the stacking fault energy high means it is easy to cross slip for a material. High stacking fault energy materials can have easy cross slip, okay. So, if I can use some second phase elements which can reduce the stacking fault energy of the material, so our creep resistance will be improved. Similar to that, some dispersion strengthening. Dispersion strengthening means what? We know some dispersions can be put in a material in such a manner that it can hinder some grain movement, okay. Here the diffusion, here we have some grain boundary associated with the creep deformation, okay. So, if I can have some segregation at the grain boundary, then there will be improvement in creep resistance. Another one is this fine dispersion, as I said, similar to that. So, we have many alloys, like these are known as super alloys. So, these super alloys can be used at that high temperature. Super alloy means what? Now, there are many nickel based super alloys are there, okay. So, nickel based super alloy means Ni3Al, Ni3Ti, that means what? We have some nickel based materials on which we are adding some amount of titanium, aluminum, etc. So, these actually make some precipitates Ni3Ti, etc., and these precipitates helps not to deform these grains, okay. So, that is how the deformation is restricted and creep behavior of the material, or rather I can say creep resistance of a material improves, fine. Then I have some creep resistant steels also there, in which also some carbide precipitates come and do this dispersion strengthening, like vanadium carbide, titanium carbide, niobium carbide, etc. Okay. So, these are all from this chapter.